Hello there and welcome to Upper 6 Further Maths. Here we're looking at polar coordinates and equations. So we can answer questions from exercise 5a. This is the first time we've seen polar coordinates. Well, we've seen something very similar to polar coordinates. Remember in complex numbers we had modulus argument form. Well, that's really quite similar to polar coordinates. You need to work out the distance, you need to work out the angle, and that's basically your polar coordinate. So what you'll be familiar with so far are what's called Cartesian coordinates. It was Descartes the mathematician who invented or formalized Cartesian coordinates, and these are the coordinates that have an x and a y value. So for example, if you've got the Cartesian coordinate 3, 4, that's 3 along and 4 up. And if you want to go left or down, you have to refer to those as negative values. So -4, -1 as the Cartesian coordinate is 4 to the left, 1 down. So anytime that you're referring to left and right and then up and down, they are what's called Cartesian coordinates. Now, polar coordinates describes the equivalent points just in a different way. Polar coordinates use the distance from the origin and then the angle from the positive x-axis. And if you have those two pieces of information, the information of distance from the origin and then the angle from the positive x-axis, you can locate exactly the same coordinates uniquely. So for example, if we had the coordinate up here, same as the coordinate up here, it would have a distance from the origin of 5, so you've got that piece of information, and then the angle of rotation round is 0.93 radians. We're generally going to be using radians here. Sometimes degrees will pop in, but generally radians is the better form to use here. So we've got a distance and an angle of rotation from always this axis here. And then that's the polar coordinate. So this here is the Cartesian coordinate and this here is the polar coordinate for exactly the same coordinate, just done differently. Distance goes first, angle of rotation goes second. It's a bit like modulus goes first, arguments goes second when you refer to complex numbers. And if you've got the point -4, -1, the Cartesian coordinate -4, -1, the distance is 4.2, just a bit of Pythagoras to work that out. And then the angle of rotation, now slightly different to complex numbers. We don't go down generally, we'll just go round the circle anti-clockwise until we meet that coordinate. So round from here to here, stopping here, that would be pi radians. 180 degrees is pi radians, or 3.14. So it makes sense to just go a little bit further on to 3.39, which will be the angle measured in radians round from this from the x positive axis. You can use radians or degrees, but radians will generally be the most commonly used in this chapter. You could go to negative going round, so don't be surprised if you ever do see a negative angle. And if you do see a negative angle, it's referring to going clockwise round from the x positive axis. Now actually, we don't use the standard crisscross way of doing a graph with polar coordinates. This is actually what a polar coordinate graph paper would look like. It would be, it would have concentric circles going round to measure the different r value, the different distance from the origin, and then it would have lots of lines coming out from the origin representing the angle of rotation round that you'll need to go. So actually quite interestingly, this is the graph paper when working in polar coordinates. So you need to know some simple formulae linking Cartesian coordinates and polar coordinates, and these come from basic GCSE trigonometry and Pythagoras knowledge. If we take this coordinate up here, the Cartesian coordinate xy, then the distance to that coordinate is r, and the angle of rotation from the x positive axis is theta. Then how can we link the letters x and y and r and theta together? Well, one way of thinking about it is that this is a right-angled triangle, and if we have adjacent equals cos times the hypotenuse, then we have x equals r cos theta. X is the adjacent side, r is the hypotenuse, cos theta, theta is the angle, so we have x equals r cos theta. So important formula number 1 has just been highlighted here. Let's do the same for the y coordinate. Opposite equals sine theta times hypotenuse. So if we rearrange that a little bit and substitute in some values, y is the length of the opposite side, sine theta is the angle, and the hypotenuse is the length r. So it's y equals r sine theta. So it's definitely x refers to cos, y refers to sine. So these are 2 important formulae. We've got 2 more to go. If we remember that tan theta is equal to opposite over adjacent, then we can inverse the tan on that and get theta equals arctan y over x, the opposite side over the adjacent side. And then if you do a bit of Pythagoras theorem, a squared plus b squared equals c squared, then it's just going to be r squared equals x squared plus y squared. So there we are, 4 important formulae that link theta and r to x and y. So have those in the back of your mind, as always, to be able to be used whenever you need them. So the first thing we're going to do now is convert from Cartesian coordinates to polar coordinates. So we'll first convert the coordinate 5, 9. So to convert it into a polar coordinate, we need to know the r value and the theta value. The reason we use r is effectively it's a radius value from the centre, from the origin. So the polar coordinate will be written as r theta eventually once we've worked out what r is and once we've worked out what theta is. So draw out 5, 9 and then use a bit of Pythagoras' theorem to work out your r value. You've kind of done a lot of this when you've worked out the modulus of a complex number. So r squared equals x squared plus y squared, and work out r, just a bit of Pythagoras theorem, 10.3. So in the polar coordinate, the first coordinate is going to be 10.3. The next thing we need to work out is the theta value, and that's just a tan calculation. So it's basically the same as working out the argument of the complex number 5 plus 9i. And we get theta is equal to 60.9. Generally we'd use radians. In this case here we've used degrees, could use degrees. So the polar coordinate, so the Cartesian coordinate is 5, 9, and that can be converted into a polar coordinate of 10.3, that was the r value, and 60.9, that was the theta value. These 2 coordinates here are exactly the same, just one's in a Cartesian base and one's in a polar base. Let's do something a little bit more complicated. 5 minus 12, for example. So again, draw out the diagram. It will be 5 to the right, 12 downwards. So we're going to have to work out the r value first. That's just a bit of Pythagoras calculation. That's 12 squared there, and we're going to get 13. And then to work out the theta value, it's arctan y over x. So it's 12 over 5, and that will give us a theta value of 67.4. That will be the angle inside here, but that's not just going to be the answer that we'll plug in straight away. Either we'll have to do a 360-degree subtraction if we're working out the angle of rotation in the anti-clockwise direction, or we can just refer to it as negative 67.4 if we to go clockwise. So 5 minus 12 corresponds to the polar coordinate of 13 minus 67.4. So sometimes it's referred to as a negative, sometimes it's referred to as the 360 minus of it. So don't forget that sometimes you have negative angles when we go the opposite way on the polar graph. Let's do another one, minus root 3 minus 1. So maybe you could pause the video and give this one a go. I'll go through it now. So let's plot the coordinate first. So it's root 3 to the left, 1 downwards. And it's the coordinate minus root 3 minus 1. So first of all, Pythagoras calculation to work out the r value. That would be 2. And then tan calculation to work out the theta value. That's going to be pi by 6, but remember the actual angle of rotation from the x positive axis is going to be pi, 180 degrees, plus whatever angle theta we've found here. So when we add pi onto this, we're going to get 7 pi by 6. So 7 pi by 6 will be the actual answer for the theta value of this polar coordinate. Okay, let's move on to doing it the other way round now. We're now going to go from polar coordinates to Cartesian coordinates. You kind of know that this is a polar coordinate because 4 pi by 3 is definitely an angle of rotation, so you can kind of tell from the second part of the coordinate whether it's a polar or Cartesian coordinate. But let's draw it on the diagram first. So it's going to be a distance of 10 away, and actually it's more helpful to draw these axes on the polar graph. 0 would start here, and then the angle of rotation would be 90 degrees, pi by 2, round to 180 degrees, or pi radians, and then round to 3 pi by 2, or 270 degrees, and then round back to 360, or 0 degrees, 0 radians. Okay, so it's going to be 4 pi by 3 radians. So if we think about it, 180 degrees would be pi radians. That would leave us with a pi by 3 left. So it would be pi by 3 radians round and a distance of 10. So this angle inside here is actually the angle pi by 3 when we draw out this triangle. So now let's work out the Cartesian coordinates. Let's work out x and let's work out y. So x here, if you remember at the top of the page here, x equals r cos theta. So just plug in 10 and 4 pi by 3. Or you could do pi by 3 and then just remember it's going to be a negative value. 4 pi by 3 would be absolutely fine to plug in there as well, and you'll get negative 5. And use y equals r sine theta again. Using 4 pi by 3 would be absolutely fine as well. Or you could use pi by 3 and just remember it's a negative value as well. So it's 5 pi by 3. So those are the two distances on this triangle. But remember that it's going to be both negative, so minus 5 root 3. Remember to interpret whether the value should be negative or positive from the diagram. Okay, so let's have a go at another one in polar coordinates to Cartesian coordinates. So we're doing 8 and then 2 pi by 3 radians as the angle of rotation round. So that's not quite pi, it's 2 pi by 3, so it would be up in the top left of the diagram with a radius of 8. So we now need to work out the x coordinate and the y coordinate using our two formulas from above. So x equals r cos theta is the first one. Just sub in the values. 8 is r, theta is 2 pi by 3. Or you could do pi by 3 if you're referring to this triangle over here. You can just substitute 2 pi by 3 in though, and you'd get 4. If you plug in 2 pi by 3, you'd get minus 4, which is actually the coordinate that it is. And if you plug in r sine theta, you're going to get 4 root 3. So 4 root 3 would be the height. 4 would be the distance to the left. So if you refer to it as a Cartesian coordinate, to go left it's minus 4, and to go up it's 4 root 3. So remember to interpret positive and negative signs from your diagram. Okay, so we're now going to move on to converting equations from polar form to Cartesian form and then back again afterwards. So the first one here is r equals 5. So this equation here is a graph where the radius is always equal to 5. You might be able to visualize that. What graph will always have a radius of 5? Well, it's a circular graph. It's a graph that will have a radius of 5 all the way around, and we know how to convert that into Cartesian equations. It's just a simple x squared plus y squared equals 25. That's just from knowledge of circle equations. You should be able to know that one pretty quickly, as long as you can have a think about what does it mean for the radius to equal 5 on a polar graph. Let's move on to part B then. Part B is not too tricky. It looks tricky, but it's actually not tricky. Cosec and sec are actually not too bad to draw, because what you do is you actually think about it as 6 over sine theta. Remember, cosec is 1 over sine, so it would be 6 over sine theta. Then multiply that sine onto the other side, and you've got r sine theta equals 6. Now, we've got a formula for that. R sine theta is equal to y, so we can now just replace r sine theta with y equals 6. So the equation here is just the Cartesian equation y equals 6. A Cartesian equation is just an equation that has the letters x and y in it without having the letters r or theta in it. So this is the equation. If we were to draw the graph, it's just the graph where the y coordinate is always equal to 6. So there we are. So yeah, r sine theta is y, and you can do the same for if it was sec, you'd just multiply by cos on both sides, and then it'd be x equals 6, for example. Let's move on to question C. Questions C and D are a lot more tricky, so bear with me. It's going to be r equals 2 plus cos 2 theta. Quite a difficult one here. Maybe we don't have any formulas where it's a double angle formula, so we might have to use the cos 2 theta double angle formula rule. And then cos double angle formula rule is this thing here, 2 cos squared theta minus 1. Let's just tidy that up afterwards. Okay, now the only way that we can bring in an x or a y letter here is if the cos theta is being multiplied by r. And given that we have cos squared theta, we have 2 multiples of cos here, we need 2 multiples of r to bring in the letter x. So what I'm now going to do, it might seem weird, but hopefully it'll make sense in a second. I'm going to now multiply both sides of the equation by r. Reason being is that then I've got 2 multiples of cos here, we'll be able to match up with 2 multiples of r here, and then I'll get an x from that. So I'm now going to multiply everything by r squared, so r times r squared is r cubed, 1 times r squared is r squared, and then 2 cos squared theta multiplied by r squared is 2r squared cos squared theta. I'm just going to break the second term up here a little bit. So it's now r cos theta, so that I can really highlight to you, we're now going to be replacing r cos theta with the letter x. We're going to be replacing these two things here as well. R squared will be pretty straightforward because I've got this third formula up here where r squared is equal to x squared plus y squared. So I'm getting rid of the letter r, replacing it with the letter x and y, which is exactly what we want to be doing in this exercise, turning it into a Cartesian equation. But with r cubed, it's going to be slightly more difficult. I'm just going to need a really complicated power on my x squared plus y squared. I'll need to do a square root to get rid of the r squared, but then to the power of 3, so it's a power of 3 over 2 on this first term here. So r squared turned into x squared plus y squared, and then the r cos theta both turned into x. And if we tidy this up, this would be the final answer here. X squared plus y squared to the power of 3 over 2 equals 3x squared plus y squared. It's a Cartesian equation. What makes it a Cartesian equation? Well, it's just the presence of the letter x and the letter y without the presence of the letter r or theta. And let's move on to the final one then. R squared equals sine 2 theta. So again, in this case, we don't have formulas for double angles, so we'll need to use the double angle formula. So that would be 2 sine theta cos theta. Similar to before, I don't have a straightforward formula for just sine theta or just cos theta. It needs to have a multiple of r on it. So I'll multiply both sides by r squared again, so that I can then split the right hand side up into r cos theta and r sine theta. Now I can bring in the letters of x and y. Now I've got an r to the power of 4 on the left hand side here, so I could just square both sides of the r squared equals x squared plus y squared formula. So this is what it becomes then. It's x squared plus y squared all squared equals 2xy, and maybe that might need tidying up a little, so it's just 2xy there. So there we are. Those are the strategies that you need to use for converting from polar equations to Cartesian equations, and it's generally by multiplying by a certain amount of r's to make sure that any trigonometric functions have an r multiplied by them. Okay, we're now going to go the other way around. We're now going to convert from Cartesian equations into polar equations. We've got 2 questions to go through here. So y squared equals 4x to do. And these ones are actually quite straightforward, to be fair. We're just going to be replacing y with r sine theta and x with r cos theta. So just substitute in the formulas from above. y replaces with r sine theta, and x is replaced with r cos theta. Expand the brackets. We could cancel out an r from both sides here. And then generally, polar equations are of the form r equals. So to turn it into r equals, we're going to need to divide by cosec squared, divide by sine squared, and in dividing by sine squared, you could effectively write that as cosec squared, because if you divide by sine, then effectively what you're doing is multiplying by 1 over sine, and we know that 1 over sine is cosec. So when you divide by sine, it's the same as multiplying by 1 over sine, which is the same as multiplying by cosec. Same would be applied here for cosec squared. And in the second part, part B, x squared minus y squared, same as before, bring in r cos theta, bring in r sine theta, and then do a bit of simplifying. So we'll expand the brackets on that, then factorize your r squareds together, and then maybe recognize that this here is a formula so this is a identity for the cos double angle identity, that is cos 2 theta. Then generally it's preferred to have r equals or r squared equals, so we'll divide by cos 2 theta, or effectively times by sec 2 theta onto the other side. So here's the final answer for part B. It wouldn't really be worth our trouble putting a square root around it, so we'll just leave it as r squared equals. Okay, so it's your turn to have a go at some questions now. Pause the video and give these two questions a go. Okay, so for the first one here, we want to convert the coordinate into Cartesian coordinates. So in this case here, I'm just going to write x equals 10 times by cos of 5 pi by 4, and y equals 10 sine pi 5 pi by 4. And I can plug this straight into the calculator, making sure it's in radians mode. 10 cos 5 pi by 4. And I get an answer there of minus 5 root 2. And for sine, let's just change the trigonometric function. Sine, I get minus 5 root 2. So my coordinate for Cartesian is minus 5 root 2 minus 5 root 2. Let's just make sure we've got that correct on the diagram. 10 would be the distance. 5 pi by 4 would be the... Yeah, that seems about right, doesn't it? It would be pi radians round to here, and then an extra pi by 4, 45 degrees, round to here. So there we are, that's the answer. And then moving on to 3D, well in this case here it's going to be r equals, I'm going to first of all turn the tan and the sec into sine and cos. So it would be sine theta over cos theta times by 1 over cos theta. Let's now multiply the cos onto the other side. So that would be r cos squared theta equals 4a sine theta. Now, ideally here we'd have another multiple of r on this side to make it r cos theta, and another multiple of r on this side to make it r sine theta. So I'm going to multiply by r on both sides now. And then I'm going to bring in the formula that r cos theta is equal to x. So that would be x squared, and then equals 4ay, because y equals r sine theta. And there we are, that's the Cartesian equation. Yes, it's got the letter a in it, but a is just a constant here. It's got the letters x and y in it. It does not have the letters r or theta in it. And there we are, that's all we're going to go through for exercise 5a. Take a pause of the video and now have a go at the questions from exercise 5a, particularly have a go at the conversions of equations and the conversions of the coordinates, and any problem solving or exam style questions in the chapter. Lovely, thanks very much for watching.